Fantastic. Okay, so here's the plan for today. Quick refresher on position time graphs, then we're going to go through velocity time graphs, and we got a lab. So that's kind of the high impact plan for the day. All right, so start with the very basics. And that's the idea that a position time graph allows you, oddly enough, to keep track of where you are as a function of time. And there's certain things you have to define, like first off, what's the reference point? You know, if I'm going to define my position within this room, am I in front of the F equals NA sign? Am I going to define my position relative to the water container, to the door? Where am I at? So that's the first thing that you have to decide. So like in the lab that you're going to do today, you're going to have a little tape timer, and we're going to say, okay, that's our reference point. We're going to define the position of this car relative to that tape timer, okay? We could define it in terms of the fire blanket, any number of things. We're just going to make it simple and go, oh, okay, here we go. Now, you don't have to start at the reference point, okay? A lot of times you do, but you don't have to start at the reference point. So when you look at a position time graph, here's a couple of things to keep in mind. One being that the slope represents the velocity, okay? So if your slope, and this is a logic problem, you go, okay, hey, right, slope represents velocity. Cool, got it, okay. So if the slope is the same, what we call constant velocity, that means your velocity isn't changing. And if the slope is changing, you're only doing one of two things. You're either speeding up or you're slowing down. So when you look at any motion in this class, there's only three possible options. Count them, only three. You're speeding up, which means that line is going to become more steep. You're slowing down, which means that line's going to become more shallow. Or you're at a constant velocity, which means the slope is going to be the same. That's it. You're speeding up, you're slowing down, or you have constant velocity. That's it. And the same thing is true when you drive your car. When you drive your car, you have one of three options. You're either making your car go faster, you're making your car go slower, or you have it on cruise control and you're cruising at 40 miles per hour. That's it. Okay? Now, like I said, eventually, yes, we will talk about changing the direction of the car. Okay? We will get into that eventually. We're just not going to get into it right now. So let's say I gave you a position time graph that starts here, and then it's going to curve, and it's going to become more steep. So it's starting shallow, and it's becoming more steep. So is this car speeding up, slowing down, or is it at a constant velocity? How do you know? Somebody said speeding up. Who said it?
It's becoming steeper.
Yeah, because it's becoming steeper. Okay? And tomorrow we'll get into what we call tangent lines. But basically, if you look at these lines, if you draw a tangent line like to a circle, we'll talk more about that tomorrow. If those tangent lines are becoming more steep, hey, it's speeding up. So what happened is that, first off, did I start at the reference point? Oh, okay. Reference point is 0. I started some distance away from it. So if this is the reference point, all I'm saying is that I started over here, and then I began to move faster. Okay? Now, once that line flattens out, what does a horizontal line on a position time graph show you?
Constant still.
What'd you say?
Like you're keeping whatever your constant was?
Yeah, okay. I've stopped. I'm at rest. I'm not moving because my position isn't changing. So anytime you see a horizontal line on a position time graph, that's a constant velocity, but that constant velocity is 0, and you're at rest. Okay. So at this point, the slope changes sign. Golden rule. Anytime the slope changes sign, you change direction. So what that means is that if I were to act this out, I'm here, I'm going to speed up, I'm going to stop for just a second, and then I'm going to come back. And I know I'm going to change the direction because the slope went from positive values to negative values. That's when I'm going to change direction. Now, at this point here, I have this constant negative velocity, and all that means is that I went past the reference point. Okay, I didn't change direction. I'm still going in the same direction. So here's my reference point. I'm here. I'm going to move over here. Stop for just a second for dramatic pause. Okay, got that. Then I'm going to move back, and then I'm going to go past the reference point, and then I'm going to stop for a second because I've got a horizontal line, and then I'm going to go back past the reference point again, and then I'm going to change direction again, and then I'm going to end up back at the reference point. So I changed direction here because I went from positive to negative. I changed direction here because I went from negative to positive, and then I changed direction here because I went from positive to negative there. So anytime you see a change in the sign of the slope on a position time graph, that means that you're going to change direction. And here I'm speeding up because the line is becoming more steep. Here I am slowing down. So I started off, okay, I'm going to kind of speed up, and then I'm going to slow down because of the fact that that line is becoming more shallow. So if you look at the position time graph, you can figure out direction. Is it positive or negative based upon the sign of the slope? You can figure out if it's at rest, if you see a horizontal line. And then you can figure out if it's speeding up or slowing down, is that line becoming more steep or is that line becoming more shallow? That's it. So you can figure out a lot of information, but you have to be able to like figure out the code. Okay, what does the code tell you? Okay, that's what you got. All right, now here's the next big set of graphs we're going to deal with, and that is velocity time graphs. Meters per second. So that's like 1, 2, 3, 4, 6, 7. Okay, now oddly enough, a velocity time graph allows you to keep track of how fast you're going as a function of time. Okay, simple as that. Position time graphs, where you're at. Velocity time graph is how fast you're going. So, let's say that when I ordered my car, I went for the nerd package on my speedometer. Instead of in miles per hour, my car indicates meters per second. Okay? So what up? I want meters per second. So I'm in my car, driving along, okay? Connor's with me. Connor happens to have a stopwatch. So, okay, Connor, here's the deal. I want you to keep track of time, and I'm going to keep track of how fast I'm going. So, the car's going to start at rest. It doesn't have to start at rest. I'm going to start at rest, okay, because Connor got in. I'm not going to make Connor jump into a moving car, okay? So, Connor's going to keep track of time. And Connor's going to look at his stopwatch at the end of 2 seconds. And I look down at my, go away. Why is that doing that? Go away. Huh. I have no idea what I just did. I have never seen it do that before in my entire life. We're just going to start over. Okay, now it went away. All right, so let's go back to here. So, Connor looks down, and his stopwatch is reading 2 seconds. And I look at my speedometer, and I'm going 4 meters per second, okay? You can run 4 meters per second. I'm old, I can probably run 4 meters per second, so this isn't that fast. So, I go from 0 up to 2 seconds, and then I'm going 4 meters per second. So, can I find the slope of that line? Yeah, okay. I can sit here and go, okay, that's 4 meters per second minus 0 meters per second divided by 2 seconds minus 0 seconds. Now, if you're in a math class, you can say, oh, the slope is 2, and you would get full credit for it because in math classes, all they worry about is just the number, okay? No one cares about the units. Physics, we do because we're just cool that way, okay? So, here's the question. When I take meters per second and divide it by seconds, do I get meters or do I get meters per second squared?
Meters.
Well, let's look at this.
Oh.
We're taking meters per second and dividing it by seconds, right? Instead of dividing by seconds, we can multiply by the reciprocal, and we get 1 over seconds. We get meters per
Second squared.
meters per second squared, otherwise known as
Acceleration.
acceleration. So I got 2 meters per second squared. So here's what's different. On a velocity time graph, the slope gives you acceleration. Okay? On a position time graph, the slope gives you velocity. On a velocity time graph, it gives you acceleration. Now, here's something hugely important. Notice that this is a positive sloping line. Okay, you're in a math class, you see a line like that. Oh, it has a positive slope. Okay, so this little section right here, I have positive acceleration and I have positive velocity. Now, here's the question. Jake, I went from 0 to 4 meters per second. Am I speeding up?
Yes.
Yeah, do not make this difficult, okay? You can't go slower than 0, okay? I've seen freshmen try. Even freshmen cannot go slower than 0. If you're at 0 meters per second, you are at rest. So if you move from 0 meters per second, your only option is to speed up, okay? So what's happening is that I am speeding up. Now, notice the sign of velocity and acceleration. Notice that I have positive acceleration and I have positive velocity. So, this is one of the most important things that you need to get. Anytime you see something speeding up, okay, and notice I'm not saying accelerating, I'm just saying if you see something speeding up, the sign of velocity and acceleration are the same, okay? Could be both positive, could be both negative. So when you see anything speeding up in this class, right away you know, oh, positive velocity, positive acceleration, okay? Or negative velocity, negative acceleration, okay? You can speed up with negative acceleration. I'll show you how that works in just a second, okay? Now, here's the other thing I want you to get out of your minds, is that, I see a pattern, cool. Positive acceleration always means that I'm speeding up. It can, but that is not going to be one of the golden rules. You can actually slow down with positive acceleration. You can speed up with negative acceleration. So one of the golden rules I am never going to have is that, positive acceleration always means you speed up, and negative acceleration always means you slow down. No, get that out of your minds. Right now, stop. No, bad, horrible. Skip that, exercise that. Do not let that begin to gain traction in your mind. The other word you are not allowed to say in this room is the word decelerate. Okay, because it doesn't make any sense, all right? Because if you're accelerating in the context of these walls in room G20, or any good physics room for that matter, if you're accelerating, all that means is that your velocity vector is changing. Could be getting bigger, could be getting smaller, could be changing the direction of this. So, and here's the other reason why we only talk about acceleration. That if you look at that big sign in the back, it says force equals mass times acceleration, okay? There is no version of that sign that says force equals mass times deceleration, okay? It doesn't exist. Now, do people use it all the time? Oh, I'm accelerating, I'm speeding up. Oh, I'm decelerating, I'm slowing down. In the common vernacular outside of a physics room, it's used, but not within the context of this room, okay? So when I tell you something is accelerated, you have to realize there's 3 potential things that could happen when I tell you a car is accelerating. It could be speeding up, it could be slowing down, or it could be changing the direction of the car. So when we say something's accelerating in this class, 3 things could happen. Speed up, slow down, change the direction. Okay, so because of the fact that I have positive acceleration, positive velocity, I'm speeding up. Now, a lot of times, and you're going to do this on the lab today, I'm going to ask you to put an arrow to indicate that this thing is speeding up. It doesn't mean that it's going up in the air. That arrow just means that it's speeding up. So imagine this. Connor gets in the car. He starts a stopwatch. Boom, press down on the gas pedal. And we're going to accelerate. I'm going to get up to 4 meters per second, and that's going to take me 2 seconds. Here's my acceleration. Now, here's the other thing I want you to get out of your minds. Acceleration is not how fast you are going. Okay, acceleration is just the rate at which your velocity changes. So all this number means is that for every second that goes by, my velocity increases 2 meters per second. So I went from 0 to 2, and then a second later I went from 2 to 4. So acceleration is just the rate at which your velocity changes. It is not how fast you are going. Okay? Get that out of your minds right now. So at this point, I'm going to take this graph and I'm going to level it off. Okay? So I'm going to level it off. Okay? Level it off. Am I still moving? Izzy, do you think I'm still moving? Yes, why?
Because your velocity is just not changing, but you can still be on the same velocity.
Beautiful answer. Okay, fantastic. Right? I just sped up to 4 meters per second, and then I'm going to maintain that velocity. So when you have a horizontal line on a velocity time graph, that just means that you have constant velocity. Okay? So here I have constant velocity. Okay? What's the slope of a horizontal line? Tyler, what's the slope of a horizontal line?
0.
So at this point, my acceleration is 0 meters per second squared. It just means I'm not accelerating, okay? I'm just maintaining a constant velocity. So when you look at the velocity time graph, there's only two things that can happen, and only two things that can happen. You're either accelerating or you have a constant velocity. It's either that velocity is changing, or it's a horizontal line and you have constant velocity. That's it. There are only two things that can happen. Now, at this point, I'm going to take this and I'm going to bring this down like this in 1 second. So in 1 second, I'm going to go from 4 meters per second to 0. Okay? 1 second. So at this point, am I speeding up or am I slowing down? Peyton, how do you know? You're right. How do you know I'm right? Or how do I know you're right?
The velocity is decreasing.
Yeah, I'm going from 4 meters per second to 0. I hit the brakes. A squirrel ran out in front of the road, and I didn't want to hit the squirrel. So I hit the brakes. Now, here's an interesting thing that's going to happen. I'm going to go from 4 meters per second to 0. Now, at this point, I'm going to draw this just a little bit. So I'm going from 4 meters per second and 5 seconds. And I'm going to go to 0 meters per second at 6 seconds, okay? Can I find the slope of that line? Devin, do I have enough information to find the slope of that line? I got 4 meters per second and 0 meters per second and 5 seconds and 6 seconds.
Yes.
So what would the slope of that line be? So I'm going to have 0 minus 4 meters per second over 6 seconds minus 5 seconds. So what's the slope of that line?
It would be, it's just like,
It's
still
going
right.
slow.
Oh, sorry.
Well, it like
It's 0 minus 4. What?
no, it's like
It just
It's
delays
still
it on
like-
the screen.
it's been delayed.
Really? That's so weird. Oh, it's like I'm in some weird matrix. Anyway, so it's like, how can you not know? It hasn't shown up on the screen. That's why. So you got 0 minus 4 and 6 minus 5. So the slope is going to be
negative 4 meters per second squared.
beautiful. Okay? I have negative 4 meters per second squared. Now look at what happened. Okay? Peyton said, oh, Mr. Burkamp, you were slowing down. Devin says, oh, my acceleration is negative 4 meters per second squared, which it is, spot on. Now look what happens. I have positive velocity, and now I have negative acceleration. My velocity and acceleration have opposite signs. So therefore, I am speeding up or slowing down.
Slowing down.
Slowing down, because they have opposite signs. So I could put a down arrow here to indicate that this thing is slowing down. So there's a couple of ways that you can look at and try to determine if something is speeding up or slowing down. I'll show you both ways. It's a personal preference how you think this through. One option is that you're into signs. Okay, hey, I'm president of the sign club at high school. Good for you. So if you like signs, you could sit here and go, oh, this is a positive sloping line, and I have positive velocity. They're the same. I'm speeding up. Over here, I have negative velocity. Excuse me, I have negative acceleration because I have a negative sloping line. So I have negative acceleration with positive velocity. They have opposite signs and I'm slowing down. Okay, so if you're into signs, go with signs. Now, here's the other way that you can do this. This is, again, you have to decide how you want to think this through. The other option is that you focus on this 0 meters per second line. Okay, this is something that Peyton kind of referenced in her answer. I'm at 0 meters per second. If this line is moving away from 0 meters per second, I'm speeding up. If this line is moving towards 0 meters per second, I'm slowing down. Okay? So if you just want to look at the line and go, hey, how is it moving relative to 0 meters per second? Oh, going away, you're speeding up. If it goes towards, you're slowing down. Or you can look at signs. It's a personal preference thing. I don't care which one you pick. Just pick the one that makes the most sense to you. Now, at this point, something important is going to happen. I'm going to take this line and I'm going to keep it going through 0 meters per second. Okay? I moved it through 0 meters per second. Did I change the sign of my velocity? Tyler?
Yes.
I went from positive velocity to,
Negative.
so did my velocity change sign? Yes. So when my velocity changes sign, what do you do? What else do you change when the velocity changes sign? Starts with the letter D.
Direction.
Yeah, it changes direction. So here's what happens, okay? So imagine this is the car. The car started at rest, it speeds up to 4 meters per second, then it's going to maintain a constant velocity, and then it's going to slow down, okay? So that gets me to this point right here. Car is at rest, speeds up, maintains a constant velocity, slows down. I didn't change the direction because my velocity is still positive. But what's going to happen here is that now the car is going to change direction. So I was here, sped up, constant velocity, slowed down, and then I'm going to start coming back in this direction. And I know that I changed direction because of the fact that my velocity went from positive to negative. So anytime, listen to me, listen to me, listen to me. Anytime an object changes direction, your velocity time graph has to go through 0 meters per second. So here's the classic example, okay? I throw this ball of twine up in the air. Did it change direction? Jade, did it change direction?
Yes.
So what did my velocity have to go through? Huh? No, not the reference point. It has to hit a specific velocity to change direction. And what's that one specific velocity it has to hit?
Sign?
Huh?
Sign?
No. Rhymes with zero.
0?
0, okay? So when something is going to change direction, the velocity has to go through 0 meters per second. So think about this. You're driving your car, okay? Hector's driving this car. And he's driving down the road. He goes, oh, man, I forgot my lunch at home. This is bad, okay? I got to get my lunch. He goes, okay, I'm not very far from home. I'm just going to back up. So imagine, here's Hector. He's driving his car, right? Okay? So he needs to change the direction. He's going along. So the first thing he's going to do is going to hit the brakes, right? He's going to, oh, right, I got to slow down. So slow down, whoop, right? His velocity has to go to 0, and then he's going to speed back up. So when you change direction, 3 things have to happen in a specific sequence. Okay, if you're going to change direction, you've got to slow down, you've got to stop, meaning your velocity is going to go to 0 meters per second, and then you're going to speed up. Okay, So if you're gonna change direction, these three things have to happen in the sequence. So here's the classic example. I take this twine and I throw it up in the air. It starts, say for example, it might start with a positive velocity. Oh, it's going up, it's slowing down. Then it's gonna hit 0 at the top, and then it's gonna change direction, and then it's gonna speed back up. I walk along, okay? Cruising along, I can say, wow, I'm gonna change direction. Okay, I'm gonna come back over here. So at that point, where I changed direction, I had to do three things. I had to slow down, stop, and then I sped back up. So when you look at a velocity time graph, anytime you see a line go through 0 meters per second, that means that you change direction. And this is what this shows. From here to here, I'm slowing down. Peyton said, Mr. Burkamp, you're slowing down. I'm approaching 0 meters per second. And then I cross 0, and then I begin to speed up, because now I have negative acceleration with negative velocity, and now I'm speeding up again, okay? And this is what this is showing. I'm going away from 0 meters per second, I'm speeding up. I have negative velocity, negative acceleration, they have the same sign, I'm speeding up. So this is one of the things I want you to get out of your minds. The idea that negative acceleration always means that you slow down. No, bad, horrible, stop, okay? The only time you're going to slow down with negative acceleration is if you have positive velocity, okay? Because then they would have opposite signs. But in this situation, I'm going to speed up with negative acceleration because I have negative velocity, okay? So that's why I said, oh, negative acceleration always means you slow down. No, stop, no, horrible, stop, no, bad, okay? Now, at this point, I'm going to draw a horizontal line. So I'm going to draw a horizontal line, meaning I have a constant velocity again. Okay? So here's what happened. If I were to act this out, here's the car. The car is going to start at 0 meters per second. It's going to speed up, maintain a constant velocity, then it's going to slow down, it's going to speed back up, and then it's going to maintain a constant velocity again. So I'm here, speed up, constant velocity, slow down, change direction, and speed back up. Now, at this point, I'm going to bring this line up to here, okay? Now, I'm going to go here, I still have negative velocity, so I didn't change direction, okay? Didn't change direction, still have negative velocity. But now I have positive acceleration. So in this situation, where I have this negative velocity and positive acceleration, that means I'm slowing down. So this is why I want you to get out of your minds the idea that positive acceleration always means that you speed up. I can speed up with positive acceleration, but I can also slow down with positive acceleration as long as I have negative velocity. So notice on the golden rules, none of the golden rules is that positive acceleration always means that you speed up. None of the golden rules are, oh, I slow down with negative acceleration, okay? It just depends upon what's happening, okay? Positive acceleration, I can speed up. Positive acceleration, I can slow down. Negative acceleration, I can speed up. Negative acceleration, I can slow down. It just depends upon which direction that you're going, okay? Got that? Cool? Fantastic. All right, now, here's the last thing, and then I'll turn you loose on the lab. So let's say that we looked at Connor when he was out running, okay? Velocity time. So Connor ran at a constant velocity, let's call it 8 meters per second, okay? So let's say Connor runs at a constant velocity of 8 meters per second, and he's going to do that for 2 seconds, okay? So 8 meters per second, 2 seconds. Boom, here we go, okay? Velocity time graph, right? Horizontal line. Connor is moving at a constant velocity of 8 meters per second, and he's going to run like that for 2 seconds, 1,000, 1,002. Constant velocity. Now, I want you to pretend that that doesn't exist. We'll get back to it, okay? Now, we know that distance equals velocity times time. Okay, we did this. This is how we figured out how fast Connor ran. We said, oh, his velocity is distance divided by time, which is just that equation rearranged a little bit. Okay? So if we want to figure out the displacement of Connor, and I'm going to use the word displacement because it's velocity times time. So I'm going to take 8 meters per second times 2 seconds. The seconds are going to cancel out. He's going to run 16 meters. Okay? There you go. 16 meters. There you go. Fantastic. Old school. Should not give you any problem at all. That calculation. Simple. Now, we're going to go back to this velocity time graph. Now, here's what I have to undo at this point. I have to undo the thought that every class, math class, you've calculated area. It's been something squared. Meters squared, feet squared, yards squared. Okay, you have had drilled into your heads that something, if you find area, it's something squared. Okay? That's what you've done. Now I have to undo this. So imagine this is a rectangle. And this rectangle has a height of 8 meters per second. And it has a base of 2 seconds. Like, whoa, Burkamp, you can't measure the height of a rectangle in a velocity and measure the base of that in time. It's weird, okay? Dimensions have to be in inches or meters or centimeters or something like that. No, it's cool. It's a rectangle. It's 8 meters per second high and it's 2 seconds wide. And we're going to find the area of this. And we're going to take 8 meters per second times 2 seconds, and we're going to get 16 meters. So, it's so weird. We get 16 meters, it's magic. Okay, so, on a velocity time graph, listen to me, listen to me, listen to me, listen to me, listen to me. This is only, and I repeat, only true on a velocity time graph. The area between the line and the x-axis gives displacement. Not distance, it gives displacement. So on a velocity time graph, that area gives displacement. Okay? Now, here's why we talk about that as displacement. Because if that is so weird. If Connor had been running at negative 8 meters per second, this line would be down here, and I would take negative 8 meters per second times 2 seconds, and I'd get a displacement of negative 16 meters. Okay? That's why we say the area is displacement and not distance, because distance is a scalar quantity. Okay? Got the idea. So, here's the story. When you have a velocity time graph, and you have a straight sloping line, which is all we're ever going to draw on a velocity time graph, this is what we call uniform acceleration. Okay? That's the only thing. We're never going to draw curved lines on velocity time graphs. Okay? And the reason being is that because F equals ma. If you have a changing force, that's the only way you can produce a changing acceleration. And that's never anything that we're going to do in this class. So when you draw a sloping line on a velocity time graph, it's always going to represent what we call uniform acceleration, which means your velocity is changing the same amount in each time interval. Okay, so can you stop that camera for just a second? Let me hand out. So what you're going to use are these constant velocity devices, okay? And they call them constant velocity devices because that allows them to charge more money. Because if they just said, oh, it's a toy tractor that moves, they could only charge like $5 because they call it, oh, it's a constant velocity device, they could charge like 30. So the first thing that you need to figure out is which direction your machine is going to go, okay? So I set it down, okay, hey, mine is going to go in this direction. You need to know that, because otherwise, if it goes in the opposite direction, it's going to fall off the edge of the table, and then we're setting in gravity, and that's a different unit, okay? So you're going to be on the table, make sure you know which direction this thing is going to go. Issue number one. Now, you're going to need a piece of tape, and this is very specific tape. It has like an iron oxide coating on one side of it. And you need about yay much tape. Okay, this is important, yay much. Not yay and a skosh, you only need about yay much tape. Okay, I know that's an imprecise measurement, but this is how much you need, yay much. If that's wrong, the whole lab's a disaster. So you're gonna have this. Then you're gonna need this, which is called a spark timer, because it measures time and it uses little sparks. So when you turn it on, what you'll see is that these little brass electrodes here start going up and down. And when they do that, they create a spark. And that's why we call it a spark timer. So there's two different settings, what they call a 10 hertz and a 60 hertz. And that's how many vibrations this thing makes per second. 60 hertz is really, really fast. That thing is going up and down 60 times per second. It's not what we want. Make sure that it's on the 10 hertz setting. Now, the on-off switch, hopefully nobody struggles with that one. So what you're going to do is that you're going to take the tape, and you have to get this sequence right. You want to take the tape and feed it through the spark timer, and when you do, there's a little arrow here that's going to show you which direction this thing is going to go. So you're going to feed that through, like so, okay? And then you're going to take a piece of tape like this, and then you're going to attach it to the machine. And again, make sure that you know which direction that your machine is going to go, okay? Because you want it to go away from the spark timer, not flying back over the top of it. That would be awkward. So, the sequence, and you have to have the sequence right. What you want to do is you want to turn on the tape timer first before you turn on the machine. Okay, so you want the tape timer going before you start the machine. Okay, so if I turn this on, okay, and you'll be able to see it's making these tiny little dots on the paper. Okay, and then I'm going to, oop, hold on, I lost my switch. Here we go. And then it's going to go away like this, and it's going to pull that tape through. So this is tough to see, but in the back. But what you'll see is that it's making a tiny series of black dots on the tape. So with this tape, there's like a shiny side and a dull side. You want to put the shiny side up because this has this iron oxide coating on it, and that's what allows it to conduct electricity, and that's how you get the tiny little black dots. So when you get done, what you'll see is that you'll see a series of dots when it was going before it started. Then you'll see a series of dots that are going to get farther and farther and farther and farther and farther apart. So this is why you want to start the machine at rest, okay? Turn on your tape timer, have this at rest, turn this on, have it go away. So when you get done, what you'll see is that here's your tape, and you're going to have a series of dots, okay, that were made before the machine started. You're going to turn on the machine, and then you're going to see dots like this, like this, like this, like this. Now, why do you think the dots are getting farther apart? Miss Elliott, why do you think the dots are getting farther apart?
Because you're accelerating.
Fantastic. Wonderful answer. Okay? Speeding up. Dots are going to get farther apart. So what you want to do on your lab, so you're going to run through 12 intervals. And this is what we're going to use as a measure of time. We're not going to use seconds, we're just going to use intervals. Okay? So what you want to figure out is how far it went in the first interval. So you're going to take your tape, And this is also one of the very few times that we're gonna work in centimeters, just because the distances are so small. So what you're gonna do is that you're gonna take your tape, you're gonna lay it out, and you're gonna measure the distance traveled between this first set of dots, where it's at rest, and this next set of dots when it was moving. So you're gonna take this, okay, and your rulers are gonna know the whole number of centimeters, the tenths, you can estimate the hundredths. So when you're measuring these with the measuring devices that you're gonna have, you're gonna know the whole number of centimeters, the tenths, you're gonna estimate the hundredths. So on your data table, here's what you've got. Time measured in intervals. You're gonna have 1, 2, 3, 4, all the way down. Displacement, total displacement, and then velocity. Okay, so what I'm gonna take this tape and I'm gonna measure that first distance from here to here. Okay, so I'm gonna lay this out and we're gonna measure it. I'm just gonna make up a number. Let's say that that's 1.40. Now, I already have the units up here at the top of each column, so you don't need to put centimeters at the end of each one of them. If you're really hardcore, it's like, oh, I like writing centimeters. Good for you. You can write centimeters, okay? Now, the total displacement is going to be how far it's gone at the end of each interval, okay? Well, at the end of the first interval, it only traveled 1.40 centimeters, so that's going to be the same. Now, for the velocity, we're going to take a cheap way out to figure the velocity. Technically, that cart started from rest, and it was speeding up. But to actually calculate that final velocity using an acceleration was going to get real complicated, and it's not what we need anyway. So what we're going to assume, because it's a really small interval of time, is that the velocity is going to be however far you went in that interval. So since you traveled 1.4 centimeters in that first interval, we're going to assume that my velocity was also 1.40 centimeters per interval. So whatever distance that you have on that first one, that's going to be the same in all three going across. Then I'm going to measure the second interval. So now I'm going to measure from this set of dots. I wish I could move my screen with my hand. So this was this first interval. Now I'm going to measure from this set of dots over to the next set of dots. Okay, so now I'm going to measure from here to here. I measure that one, it's going to be more because it was speeding up. So I measured that one, and let's say that was 2.00. It was exactly 2 centimeters, okay? So I have to write that as 2.00. The total displacement is going to be how far it's gone. So that total, whoa. That got real weird. Okay. No idea what's going on. Okay. So, stop. Okay. So, my total displacement is going to be the sum total of how far I've gone at the end of the second interval. So I'm going to take 1.4, I'm going to add that to 2, and I'm going to get 3.40. So, to get this column, you take what you had before, add that to that, so at the end of the second interval, we've traveled 3.40 centimeters, okay? So this is going to be running total. Now, this column over here is going to be however far I went in that particular interval. So my velocity in that time interval is going to be 2.00. So these two columns here are always going to be the same number. They represent different things, but if numerically they're the same. So at the end of the third interval, let's say that I went 3 centimeters. So that would be 6.40, and that would be 3.00. Okay? Be consistent on how you measure these. Now, you need 12 intervals. When you get done, you're going to draw two different graphs. You're going to draw a total displacement versus time graph, and these times are just going to be intervals. And you're going to go from 0 to 12. Okay? So when you get done with this graph, at the end of the first interval, like for example with this data, I went like 1.4. At the end of the second interval, I was at 3.4. At the end of the third interval, I was at whatever that number is. So this is going to be total, and I emphasize this. This is total displacement versus time. So what you're saying, at the end of each interval, you're going to plot how far you have gone from this timing device, which is our reference point. How far have you gone at the end of each interval? Okay, so that's going to be that running total column. Oh, at the end of the 10th interval, I've gone this distance. Okay, when you get done, what you should see is that it should look something like this. You should have a shallow part at the beginning because that's when it's speeding up. Then, hopefully, your velocity becomes pretty constant, and then it becomes a straight sloping line. Okay? So that's roughly what that graph should look like. Now, the next graph you're going to draw is the velocity versus time graph. Here's going to be in intervals. This is going to be in centimeters per interval. Okay? This graph is going to start at 0, 0. Okay? 0, 0. So what this graph is going to look like, hopefully it does something like this. Okay? Where you're going to start at 0. Okay. It's going to start at 0, and then it's going to go away, indicating that speeding up, because I'm going away from 0 meters per second. I'm also having positive acceleration with positive velocity, which means that it's speeding up. And then it's going to probably have some fluctuations to it, okay? We really don't have pure constant velocity devices, but they're pretty close. So there's a bunch of things that you want to do on this velocity time graph, okay? You want to indicate if it's speeding up or slowing down. So basically, if that line is going away from 0 meters per second, put an up arrow, indicating that it's speeding up. If it's going back towards 0, put a down arrow. Oh, I'm slowing down. Speeding up, slowing down. That's one of the things that you want to do. You also want to indicate if the acceleration is positive or negative. Oh, here I have positive acceleration because it's a positive sloping line. If it's sloping down, I'm going to have negative acceleration. Okay? So, that's what you're going to do on number 3 here. Indicate if the acceleration is positive or negative each region by either using a positive A or negative A. Now, on number 4, you want to calculate the average velocity for the 12 intervals. So remember, we talked about this yesterday. Average velocity is your overall final position minus your initial position divided by time. Well, this is easy. What's your initial position going to be? 0. Your final position is going to be how far you've gone. That's going to be that middle column at the end. And then you're going to have 12 intervals. So to get your average velocity, take your overall total displacement minus 0, divide it by 12, and you're going to go if that's your average. Don't add up the velocities and then divide by 12. You can do it that way, but it's a god-awful amount of work that you don't need to do. So to get that average velocity, take the sum of what you have as your total displacement, divide that by 12, there you go. So what you're going to do here is that you're going to draw that as a horizontal line to indicate that's my average velocity. So when you get done, this is what your velocity time graph is going to look like. You're also going to draw that on your position time graph. But on a position time graph, that's going to be a diagonal line. So on your position time graph, you're going to draw that average velocity as a straight sloping line because that's going to be that slope. You got a bunch of questions to answer. When you get down to question number 5, write an explanation to describe what can be deduced by the shape of the position time graph. Okay, so you're going to look at your position time graph and you're going to go, wow, what can I conclude? So here's what you're going to, this is what I'm looking for. Oh, at the beginning of the graph, it's shallow and becoming more steep. That indicates that it's speeding up. So when I tell you to talk about the shape of the graph, guess what you want to talk about? The shape of the graph. So you're going to say, oh, it's speeding up here because the line is becoming steeper. Then hopefully, eventually, you get a straight sloping line on your position time graph, which is going to indicate that you have constant velocity. Then on number 6, you're going to do the same thing with the velocity time graph. So on your velocity time graph, which is going to look something like this, you're going to say, oh, at the beginning, it was a sloping line, indicating that it was speeding up. Then the line kind of becomes horizontal, which indicates then we're going to have constant velocity. Okay? That's what you want to look for. Okay, I'm done. You're on your own. There's like 16 of you, 4 groups. Everybody's going to, each group is going to have their own tape, but everybody can, you don't have to generate a tape for everybody. Just use that same information, that tape for one group. If you're not sure if you're doing it right, ask me and I will tell you. Let's go do science.